electric universe, we see the cosmos as waves and fields. We see matter and gravity as a consequence, not the cause. This perspective allows us to see everything with fresh eyes. I've heard the term paradigm shift used several times. I don't think that's an adequate term. I prefer the word enlightenment because that implies a discovery of a higher truth. Our enlightenment is a return to the finding empirical truth with our senses. And by that enlightenment, the simple elegance of our universe can be revealed. I'm going to show you simple elegance in the Earth's geology, how to recognize at least one set of evidence for the electrical sculpting of our planet. It's called Arc Blast. The Arc Blast model provides evidence and a means to verify electrical scarring on Earth. It provides insight into the electrodynamic forces at work in the solar system and its coupling with the Earth. And it provides a key theoretical foundation for building a comprehensive model of an electric Earth. To electrical workers, a high voltage fault is called an arc flash. It typically follows a surface conductive path, skimming over non-conductive solids in a layer of atmosphere that forms a halo of ionization around the solids. The discharge across these insulators demonstrates in the image how it skims across the surface. Sometimes it contacts, sometimes it forks, sometimes it braids around each other, the filaments of the arc. Arc flash creates a shock wave, and that is the arc blast. Arc blast occurs because the arc is at temperatures of 35,000 degrees Fahrenheit. It melts and it ablates and vaporizes matter in its vicinity. Copper conductors vaporize instantaneously, explosively increasing in volume almost 80,000 times. It's the most explosive event imaginable when you can realize there's no limit to how big an arc can get, commensurate with the stored energy and potential difference that creates it. The explosive volumetric expansion creates a shock wave, and that is what kills electricians more often than electrocution. Planetary scale arc blast occurs in the crust and in the atmosphere, where the conductive layers of this big capacitor we call Earth form. It's the same region we see thunderstorms form today and volcanism from 60,000 feet in the atmosphere to some distance below the crust. It's where the charge accumulates and discharges. The landscape is sculpted not only by the discharge, but by hydrodynamic forces created by the shock event. In a thick, viscous atmosphere like Earth's, this has to be the case. And the evidence is in coherent landforms like these. In particular, the triangular buttresses that are shown here in this coherent landform that was created in a single cataclysmic event. These are the result of supersonic shock, supersonic winds, and electromagnetic effects, all created in a single arc blast event. There's no question that landforms like this are the result of a single coherent event. It belies any uniformitarian process. The triangular buttress form normal to the trajectory of the shock wave that created them, and they're layered in place by winds. This is how it happens. The colorized simulation in the image shown, it's a colorized simulation of a supersonic projectile passing over water. The image was produced at Los Alamos Laboratories. I've annotated it to show some of its features. The colors represent density, with purple being the background density of the atmosphere, reds show high-density regions, blues show low-density regions. In an arc blast, the projectile is a bolide of plasma in an arc, radiating temperatures 6 times that of the sun, traveling at supersonic speeds. It creates a shock wave with pressures of thousands of psi. In region 1, the bow shock strikes the land, and it's both a blowtorch and an anvil, melting, vaporizing, and ablating the land below it. In region 2 is a reflection of the shock wave. It rebounds from the land, drawing a low pressure zone behind it. The expanding gases from the blast explode into a violent mushroom cloud called a Richmeyer-Meshkoff instability. In region 3 is a rooster tail of very low pressure that follows this shock wave. This rooster tail is like the rooster tail behind a speedboat, and it sucks up the molten material from the crater and forms the core of a mountain. Region 4 are standing reflected shock waves. They resonate with the mountain's formation, and they leave distinct marks on the land, like the coherent triangular buttresses I just showed you in the last image. A closer look at region 2 shows the mushroom cloud expands in the reflection of the primary shock wave. It has the inertia of the reflected shock and the violently expanding gases to form an updraft at its core that draws supersonic ground winds from below. They flow in perpendicular to the trajectory of the primary shock wave. This violent updraft begins in the rooster tail, which draws a bladed material from the blast zone and redeposits it in the wake. And here's an image of a very simple linear hill that's formed in this manner. But this process can form much more complex and larger shapes. The triangular standing waveforms created by the primary shock wave form plenums for the ground winds, directing their flow like nozzles. A shock wave is an incredible shear zone of pressure, temperature, density, and current. Standing waves don't travel. They stay in place with the energy coursing through them. I like to think of it as an entire tsunami in a pane of glass. In the inflowing winds, the shock waves are like walls of steel. In a sustained event, these triangular buttresses keep crawling outward, building outward into ridge lines, retaining the shape of the waveform that molded them. So I'll talk about supersonic waves and the effects of those, and then I'll show you some examples in the mountains that are exact replicas of these waveforms. Supersonic waves are longitudinal waves that expand behind the projectile. The angle they make between the trajectory and the shock radiation is called the Mach angle. The Mach angle is proportional to the Mach speed of the projectile. So if you can look at a landform and determine the original incident shock Mach angle, you can get information about the speed of the bolide that created it. When the shock wave strikes ground, it reflects at an angle relative to the angle of attack of the Mach, and to the Mach angle. So again, the relative angle, or the rebounding angle will give you more information about the trajectory and speed of the shock wave that created it. Standing triangular waveforms created by reflection are an inevitability of the event. The wave travels on a transverse carrier wave called the propagating wave. As the shock rebounds, some of its energy is absorbed by the surface, and most of it, is rebounded. The energy of the shock dissipates over time in a predictable way. As the mushroom cloud rises, drawing supersonic ground winds through the shock envelope, the winds provide sustaining energy and they keep it alive. So this set of standing waveforms gets created, and as that energy is reverberating through it with these supersonic winds, it's resonating, and that's a source of free energy to this vacuum cleaner that's sitting over the land. Shockwave behavior has been studied for years. If the projectile changes direction, the shock radiation does too, in predictable ways, resulting in new shock reflections and expansion and compression of the waves. Shock waves can fragment, creating expansion fans. Excuse me. Or they can reflect off of each other, creating new reflections. New reflections continue to form like a hall of mirrors to the nth degree until the energy of the shock dissipates. The propagating wave is a transverse wave that vibrates the land seismically. The shock wave is a longitudinal wave, so it compresses and expands like an accordion. The resultant waveform that forms over the land and forms this shock envelope is a superpositioning of longitudinal and transverse waves. So the pink waveform at the bottom is the resultant waveform that forms the shock envelope. Expanding and compressive waveforms are embossed on the flanks of mountains exactly as they were formed by the winds of the shock wave. This is an image of a mountain that's in China, and it shows the expansion and compression on the waveforms. This is an image of a mountain in Argentina that does the same thing. The amplitude and wavelength change inversely with frequency. This is a property of waves. The waveform always meets at the base to form a continuous row of triangular buttresses. Mainstream science has sort of an explanation for these features. The land expands and slip faults form, and the broken land rises into mountains and falls into valleys. It's called the horse graben model. And it's used to explain most basin and range regions. Then seismic waves are theorized to roll beneath these mountains and create features that some have interpreted as these triangular buttresses. Mainstream theory says earthquakes deep below form longitudinal P waves that rise to the surface, and transverse S waves that rattle the ground like that. And the result is an undulating surface wave. On the lower right, there's two surface waves shown. One's called the love wave. The love wave ostensibly jumbles fault blocks into triangular forms like we're seeing. And the Raleigh waves are believed to compress and expand fault blocks into a rolling shape. In both cases, it requires fragmenting of the mountain into these small fault blocks, like child's blocks that get jumbled around. I don't know, but how such seismic rolling waves beneath a mountain could roll beneath and form triangular buttresses that wrap around the end like are shown on this mountain. If a wave, a surface wave, is rolling beneath this mountain longitudinally, it's going to keep on going in a straight line. It can't turn around and wrap around the mountain and keep forming these waves. Now there's another possibility, and that is a shock wave that comes from below. And it would have to come basically below this mountain and send these radial waveforms up the side. But that doesn't really make sense. It doesn't comport with what we see. The triangular buttresses are layered in place. Seismic waves can explain buttresses that are layered in place. There are no fault blocks here. Buttresses are stacked, layers blown into place by hot supersonic winds. You might think, well, this is an ancient beach or sedimentary layers of an ancient lake that have been uplifted and somehow serrated into triangular waves. But no, these are vertical buttresses in Mexico, and they're all granite. So it's not an ancient beach. It's not sedimentary. These are layered in place by supersonic winds. You'll find them at a low repose in some strata, and you'll find them almost vertical in areas like this. You'll find them in sandstone, you'll find them in granite, you'll find them in every type of rock. Excuse me. Evidence so far also suggests that most of these buttresses are layered in place in a molten state. And this image shows the putty-like formation as they were blown into place. Proof that winds form buttresses is evident in this picture, where one mountain has canceled the one behind by blocking the ground winds. The coherence of this landform is undeniable. Buttresses face perpendicular to the wind direction because the reflected waves are parallel to the trajectory of the shock wave, and they form windows for the winds to flow in radially normal to the shock wave. More evidence of wind formation is apparent in the stratified layers of pressure ridges that form concentric rings around the mountains. These pressure ridges can be seen to stack in one way on one side and stack in the other way on the other side, clearly showing two different wind directions coming to meet at the mountain. The amount of energy absorbed by the substrate is apparent too in the waveform. Hard substrates reflect sharper angles like these, and soft surfaces have a lower modulus of elasticity and absorb more energy. They also feed back vibration out of phase to the shock envelope, creating rubbery-looking buttresses like these. Now here's a mountain core that looks almost totally incoherent, and yet it has these perfectly formed, coherent, sorted, and layered waveforms welded to its flanks. I mentioned before that shock waves press against each other in compression. And here's an example of where a waveform is squeezed by its neighbors into a semicircle. In the next layer, it's been canceled out, and the adjacent waves have joined wavelengths to fill the gap. Even more compelling evidence of triangular buttresses are the result of, that they are the result of shock waves is harmonics. Harmonic waves always form in integer multiples within the fundamental or original wavelength. Shock wave harmonics are created by instability. This is a Schlieren image of a wind tunnel test that demonstrates. In the first frame on the top left, the speed of the wind is Mach 2. As the frames progress, the wind slows and instabilities form. Vertical waves called normal shocks are forming. They are standing waves as well, but they slowly migrate through the triangular reflected waves as the speed of the wind changes. Normal shocks interfere with the triangular waves and cause them to shatter into multiple reflections. In the last frame, you'll see 7 triangles, where at Mach 2 in the first frame, there's 1.5. Note the angles of the reflected waves have changed, the frequency has gone up, and the amplitude has gone down. So here's an example of the normal shocks that migrate, and they were impressed into the mountain core. The triangular buttresses are stacked below it, but they're on top of these. These slices don't cut through. So the triangular buttresses were blown in after these normal shocks passed. The normal shocks are parallel and almost equidistant across the mountain core. They're close to vertical, but in this aspect, they appear a little bit more angled than they really are. This is another example that shows normal faults and some very pretty mineralized layered harmonic waveforms. Now I'm going to switch over so I can show you. Right here is a normal fault, and you can see it slices right through the buttresses that are formed in the center here. You can see it all the way down the mountain. Right over here is a second normal fault impression. It's a little bit distorted because there's this erosion canyon over here, but you can see it at the bottom, and you can see it beginning at the top. But in the center, it's covered over by the waveforms. And then right over here is another normal fault that's hardly discernible because it's almost completely covered over from top to bottom, but it's there. Each of these, again, is parallel to each other, same shape, almost equidistant. But what's unusual is that this waveform happened after these were created. This one happened before these were created. So there's a temporal relationship between these normal shocks as they pass through and the buttresses as they were layered in place by the winds. Here's a set of harmonic reflections in a soft substrate in North Africa, and this shows the harmonics. Each major waveform breaks down into 2 or 3, and then each of those break down into 2 or 3 or 4 or more. These mountains have reflections everywhere. Note that the ridge lines build outward until the waveform shatters into harmonics, and those can continue to build smaller ridges. Here's another example of the harmonic formation. And I'm going to switch here again to be able to point this out. First, you have the large waveform that comes across here, even extending out of frame. Right here is where a normal shock is hit, right at the apex, and left an impression, and caused this waveform to shatter into these 7 harmonic waveforms. Now, there's actually an 8th, but it goes out of frame. Then each of these 7 waveforms shatter again, so you get multiples of 2 or 3 or more in here. And right here, I've circled where 7 tiny little waveforms have formed in a straight line within the wavelength of their parent. Here's another good example of how the waveforms shatter before they form a new layer. Because in this one, I'm going to have to go back to the, show you what I'm talking about. Where the arrow is right here, this last layer, before it shatters into these harmonics, has started to serrate because the harmonic reflection has begun. And you can line up the apex of these serrations with the harmonics below. So this buttress was layering outward, and then it started to shatter, and it serrated the edge just before it broke into harmonics, into a new layer. With sustained energy, the wave envelope acts as if it's alive, building ridgelines that cancel each other out, jostle each other around, and split into harmonic multiples. Here, the center ridgeline is canceled by its neighbors. A normal shock has passed through, and you can see its progression in a stepwise manner, creating zigzags across succeeding layers and causing the waves on the left to expand and cancel the center wave. This is where the normal has passed through, migrating through, and it creates kind of a zigzag because it makes an impression here as these layers are being formed, and then it jumps over here as these layers are being formed. So that's the zigzag pattern as this normal shock went through. It canceled out this center ridgeline, and this ridgeline widened to take up the space. Note how ruler straight these waveforms are on the outside of these ridgelines. They remained unchanged as this cancellation took place. Doesn't want to respond to my finger for some reason. These harmonics look like the embroidery on a shirt I wore back in the early 70s. The material is layered and sorted according to its dielectric properties by the electromagnetic fields that are the engine for the big Kirby vacuum cleaner that created it. Now, let's see if you're as good as I am at seeing Jesus in a piece of toast. Take a careful look at this unstable waveform. It's being pinched in at the top around this circular feature. And harmonic reflected waveforms are forming triangles down at the bottom below that circular feature. The feature of a circle is a low density feature. Now look at this buttress in northern Arizona. It's almost a spitting image of the waveform. There's the hole where the low density region is. It's pinched in at the top, just like in the Schlieren image. And you can see the waveforms, triangular buttresses that have formed below in almost the same configuration. So I'm going to back up so you can take a look at that again, if I can figure out how to do that. There. Take another look at the hole, the pinching, the triangular waves below, and take a look at the hole in Arizona. These low-density holes are quite common if you look around. Here's one in Iran. This is where two holes have begun to form in succeeding layers on these buttresses in Utah. Now here's another test for your pattern recognition abilities. This is a road cut in Iran. It's not a triangular buttress. This is a completely different shock feature. This is where the initial bow shock rebounded from the surface of the land and folded into its reflected wave. There are particular morphology of this reflection at the boundary layer. As shown in this diagram, excuse me, I think I'm going to have to switch again. So this is the boundary region reflection of a shock wave. This is the incident shock coming in, and it takes this kind of a curve downward as it bends and reflects. And then the reflected shock is coming back up almost straight. The reflected shock forms some expansion right here, which creates these transmitted shocks down here inside the wedge. These transmitted shocks, you can see, have a dip to them. Also, another feature is the lambda foot right here at the bottom. This is the bottom of the reflection, where some of the energy is dissipated into the soil below. And I've also annotated in red myself because thank you, because it was not on the original. I don't know how to do this with the microphone. Thank you very much. I've also annotated that was not on the original diagram another shock feature, which comes down here normal to these transmitted shocks. So take a good look at that diagram. When I get my finger to work. And here's another image of this. This is the same road cut in Iran. It's just a different perspective that allows you to see a little bit clearer the features. And almost every feature is here. This is the incident shock curving downwards and reflecting back. The reflected shock is almost straight. This is the curving transmitted shock. Lambda foot's right down here. I'm going to go back so you can take a look. This is the original photo I showed, a little bit closer up. Oh, and I failed to mention the transmitted shocks right here have also formed the same dip in the wedge. Now, if pattern recognition isn't your thing and you don't trust in that, don't trust what your lying eyes show you, how about some theoretical physics and differential equations? Dr. Mark Boslow is a physicist and a geophysicist at Sandia Labs. He's a recognized expert on airburst meteors. He studied Chelyabinsk and Tunguska. He and his team used Sandia's supercomputers to simulate an airburst meteor. Here's Dr. Boslow in front of his simulation, pointing to the region of the mushroom cloud, where the inflowing winds are actually coming in at the ground. He's a graduate of Caltech and Colorado State. He's a made guy in the mainstream. He has YouTubes, popular articles, and peer-reviewed papers to his credit. But he's a gravity guy. He gives TED Talks on the dangers of global warming and advocates against global warming deniers. So I doubt he's going to come to an Electric Universe conference soon. But his insights and his work are directly applicable to Arc Blast. An airburst meteor, as he defines it, is when a cometary fragment or an asteroid enters the Earth's atmosphere and it blows up in the air. But it doesn't fragment into pieces of rocks that hit the ground. It atomizes into a plasma bolide. And that plasma bolide continues in the trajectory of the projectile that it came from, pushing a shock wave in front of it. And it's that shock wave and plasma that hit the ground and create the airburst features. And that's what he speculates happened in Tunguska. And he's probably right. But he hasn't looked at all these landforms, because the features that are created, the triangular buttresses, the ablation zones, the pressure ridges, they're all evident on this mountain here. And it's in Syria. It's a 100-mile-long curvilinear mountain. And there's no way that a projectile coming from space can create a curvilinear mountain. Nor can it create 90-degree radial bends like these in Siberia. Nor can it create diverging paths like these. Nor can it do a sudden change in direction. Now this is in Iraq, this astrobleem, and it looks like two different ones, but it's actually one. You can look very closely. There's connection between in the middle, but it's a sudden change in direction, and there's no way that a cometary fragment or asteroid could do that. Here's a set of astrobleams that apparently all happen simultaneously, but they're pointing in different directions. I can't confirm to you that these all happen simultaneously, but if we had the field work to do it, and to go out and look at these blast zones, these ridge lines, the shear zones between them, I believe we could determine that it was a simultaneous event. The other thing are mountain arcs, continental-sized mountain arcs. The triangular buttresses, expansion fans, all these features I've been talking about, you can find in continental-sized mountain arcs, and you can find them in mountain cordilleras on all the continents, except Antarctica, because there's too much ice to tell. So it can't be a projectile from space. These have to be created, in my opinion, by something that can sinuously curve around like an arc. I'm going to show you another feature. It's another shock feature on the land. It's called an expansion fan. Now, when a trajectory, a supersonic projectile's trajectory changes, it has an impact on the shock wave. So if it makes a convex corner, it will create this oblique shock, which is a compressive shock. If it makes a concave corner, then it fans out into what's called a Prandtl-Meyer expansion fan. This is a Prandtl-Meyer expansion fan. Now this feature that I've annotated there is about 10 kilometers long. The fan is a series of ridge lines that were pressure ridges formed as what apparently looks like the arc took almost a 180-degree turn. And as it curled inward, this fan expanded out from tangentially from the curve. Here's a closer view. The triangular buttresses are shown very clearly on the inside of the mountain arc, and they're also shown on each of these fan ridge lines. On the right-hand side of the fan, there's a big field of ablated material. It also shows the shock effects of high-speed winds. On the inside of the mountain arc, you can see that the triangular buttresses have built long ridge lines and then broken into harmonics at the very end. And you can also see the pressure ridges inside the arc from the high-speed winds. On the fan itself, you can see the triangular buttresses, which I've annotated in purple to highlight them, and that they have also broken down into harmonic waveforms. This is a close-up that shows the layering of the buttresses in the expansion fan. And it appears to me that they are layered in place in a molten state. You can see that erosion is fairly minimal on these features. There are ruler straight ridge lines. The layering is also evident on the reverse slopes, where you can see the stratification. And here's another view. Each one of these pressure ridges, as you move to the right, because the wind was coming from the left, and as they began to form, the ones upstream in the wind grew and blocked off the other ones. So they're successively smaller as you move to the right because they got less wind. The wind starved from the left side. It's apparent this whole structure is coherent and was created in a single event. And this is a look at from the other angle so that you can see the fans and slightly curl up at the ends. Okay, so that's all the pictures I have in the presentation for now. What I've showed you is 12 different points of evidence today. There are more features that I haven't had time to show, but if you look at the articles and at the space news that we've put out, and in the future that we'll put more out, we'll discuss these. All of these 12 points comport with a theory of an arc blast formation. You have the triangular buttresses themselves that are the result of supersonic shock reflection. You have expansion and compression. You have wind layer deposition and orientation. You have concentric pressure ridges, normal shocks, interference and cancellation, unstable waveforms, boundary effects of shock reflection, curvilinear paths and expansion fans, and most of all, you have coherence. Other evidence that I haven't shown includes shock features and thermal stratification in the rock that supports an arc blast model, micro reflections that create square or diamond patterns, especially in cap rock. The geology tour will probably see some of that. Mountains and hills of stratified wind-blown ejecta, evidence of when two or more arcs physically interfered with each other, and their interactions recorded on the landscape too. Wind effects such as shear zones, rotation, and falling subsonic winds that form Kelvin-Helmholtz roll-ups modify ridge lines. This isn't a complete theory. It's still in progress, it's still being formulated, and there's a lot more to learn. We need to understand more about the magnetohydrodynamic effects of an arc blast. We need to understand more about the dielectric sorting and possible in situ formation of rock. We need to understand more about arc morphology, where this arc comes from to create an arc blast, where it's going, how it does this, what type of arc is it, what type of event causes it. I don't know, but as I try to envision what one of these arcs would be like, it's not a lightning bolt from space. You can look at the moon or Mars or Mercury and see hexagonal craters and rills and all this stuff that really looks evident that they were lightning bolts from space, Birkeland currents, carving those kind of features, normal to the surface. But that's not what we're seeing here. We're seeing these hydrodynamic effects. I believe what's going on is that the current is in the crust. It's in the magma. I think the magma is the plasma of the Earth. And in some extraneous event happens, whether that's from a comet entering the solar system or planets out of place or just a big solar flare, the system gets amped up, and I think there's this reciprocating current in the magma. And it heats up because it's getting amped up, and that's creating volcanoes. It's creating magma to vaporize. It's breaking the conductor that this oscillating current is in. And so now there's stored energy somewhere else that wants to reciprocate back, and its normal conduit is broken. So it finds a new path. And I think that's when we see arc flash. I think that's when it crawls out of the Earth's crust and blasts into the atmosphere. And it creates these features and some other features too. At least that's my opinion, and there's things that we have to learn more about that to see if that's a reasonable conjecture or not. I think what Bruce Laybourne showed earlier could shed a whole lot of light on how this might happen, how these oscillating currents might happen, where they might come from, where they might be going. There's a relationship with volcanism, seismic, and other phenomena. Arc blast doesn't occur in isolation. It's happening when other things are going on. And the landforms reflect that too. And it makes it complex. Some mountains are very pristine where you see triangular buttresses and it's quite clear what happened. But in other cases, it's not, especially when ablated material covers things up. There's also something to know about the chronology of events that created these things. And I think there's a lot to be learned from geology in that. But I also think there's something to be learned from mythology, because I think some of these events were witnessed. And I think if you look in the record, I think there are places where you can find in the Bible and in the mythology of dragons from the sea, Leviathan, Neptune, Poseidon. I think these stories are talking about arc blast events. Waves carry information. They are information. It's how I'm communicating to you now. It's how we always communicate. Standing waveforms frozen in place at the time they were formed hold scads of information about how and when they were formed. What better example of the simple elegance of the electric universe could there be? Thank you.